Hello, teachers and students. My name is Mingjing. I come from the Mongolia University of Finance and Economics. In the next few minutes, I'm going to present my paper, an improved computational method for solving partial differential equations arising from communication engineering. Before my presentation, I'd like to thank the reviewers for their efforts to improve the quality of this paper. Now, let's begin. As we know, the numerical methods of partial differential equations plays an important role in many applications, which have been frequently applied in many areas, such as communication engineering, fluid dynamics, economics, quantum mechanics, fluid mechanics, chemical reactions, physics, and electrical networks. Many researchers have utilized various numerical methods to solve partial differential equations. In reference to, the authors used the optimal auxiliary function method to solve partial differential equations, which was extended to generate partial differential equations. In reference 3, Jonet used the differential transform method for solving Burke's partial differential equation. In reference 4, Radek solved partial differential equations using the lattice-Boltzmann method. In reference 5, Wang employed localized Chebyshev collocation method for solving elliptic partial differential equations in arbitrary 2D domains. In reference 6, Young adopted the two-step MPS-MFS ghost point method for solving partial differential equations. In reference 7, Han used a derivative-free method for solving elliptic partial differential equations with deep neural networks. In reference 8, Ren used a higher order non-local operator method for solving partial differential equations. In reference 9, Stephen solved the conservation equation by using the symmetric multiple reduction method. As we know, reproducing Keno method is a very good method. In the previous works, in reference 10 to 12, the authors presented the traditional reproducing Keno method for solving all kinds of partial differential equations. Nevertheless, the traditional reproducing Keno method cannot get accurate numerical solutions. So the traditional reproducing Keno method must be improved. In reference 13, we improve the traditional reproducing Keno method by the piecewise interpolation technology, and the paper is published in AMC. Through we obtain the higher accuracy numerical solution by the piecewise interpolation reproducing Keno method. However, the more piecewise we choose, the higher the absolute error is obtained. Sometimes the absolute error of dividing 50 and 100 tables are almost the same. But the latter one requires much more work than the former one. In order to solve this problem, we are ready to combine the advantage of adaptive algorithm and precision of the piecewise interpolation reproducing Keno method. The main purpose of this paper is to find an effective and time-saving computational method through adaptive technology. In the smooth error, we don't need to take too many pawns. In the steep error, we need to take a lot of pawns to ensure the accuracy of the calculation. Our content has three parts. First part is the reproducing Keno method. The second part is a numerical example. The last part is conclusion. First, I'm going to present the part 1, reproducing Keno method. In order to present the new method, we consider the following equation arising from communication engineering as following. The linear space and their inner product defined as follows. So they are producing Kenos Rs1T, Rs2T, and Rs3T have been expressed in this paper. Before using the traditional reproducing Keno method to solve the equation 1, it is necessary to harmonize the initial and boundary conditions. Then we get the new equation and denote the exact solution of the new equation by uxt. With the initial condition and the boundary condition ux0 equal u0t equal u1t equal 0. So the solutions of the equation 1 are equal to the solutions of the equation 2. By the reproducing Keno method, the exact solution ux is given by reproducing Keno functions in a series exponential form. The approximation solution is expressed by n-term summation of reproducing Keno functions. However, the satisfactory results cannot be obtained by directly using the above method. So the adaptive piecewise interpolation is used. The main idea as follow. Firstly, the reason xt in D is divided into n small reasons. And then the numerical solution of the first small reason is solved by using the traditional reproducing Keno method. So the boundary value of the first small reason is the initial value condition of the second small reason. By parity of reasoning, the boundary value of the last small reason is given. Secondly, a maximum absolute error dirt is set in each reason. When the absolute errors are greater than dirt, the reason will continue to divide until the absolute errors are smaller than dirt. Finally, when the absolute errors are smaller than dirt, the dividing is stopped, and the optimal small reason is obtained. Then the traditional reproducing Keno method is used to solve the problem in each reason to obtain the numerical solution of the whole reason. In part 2, the numerical example is presented. Considering the following partial differential equation with the initial condition and the boundary condition ux0, u0t, and u1t. The exact solution of the equation 3 is uxt. Fx is obtained by uxt. By mathematics 7, let n equal 10, t equal 1. Figure 1 shows the exact solution. Figure 2 shows the numerical solutions by the traditional reproducing Keno method. Figure 3 shows the numerical solutions by the new method. Figure 4 shows the numerical solutions by the new method. The blue line in Figure 2, 3, and 4 is the exact solution. Figure 5 provides the absolute errors by the traditional reproducing Keno method. Figure 6 provides the absolute errors by the new method. Figure 7 provides the absolute errors by the new method. It is obvious that the new method is better than the traditional reproducing Keno method. And the more number we piece, the more accurate results we get. In the last part, I have a conclusion. In this paper, the adaptive piecewise interpolation reproducing Keno method is used to successfully solve a class of partial differential equation, which is widely used in solving science and engineering problems. The two numerical examples show that the more number we piece, the more accurate results we get. Moreover, the new method presented in this paper can solve more complex partial differential equations, such as the following time fractional partial differential equations. Thank you for watching, and my email is presented. If you have any questions, please send me an email.